become operators as well. This becomes an annihilation operator, and this guy, where the complex conjugate becomes an adjoint, becomes the creation operator. For a quantum of momentum k. And we just quantize it the same way that we quantize the harmonic oscillator. We impose the combination relations. That's the important algebraic structure that we have in PFD. As I said, these are not really operators. In loose terminology, we call them operators, but they're operator-value distributions. You can already see this here, where you've got an operator, unit operator 1, and then you've got a distribution in front of it. So whenever you smear it with a test function, what you get is a distribution. And that's going to be the source of a lot of issues, as we shall see. And the way we construct our Hilbert space is as the Fock construction of the one particle Hilbert space. Okay, so I told you how to build this Fock space. And we've got a one-to-one mapping between H1, so the Hilbert space of all one particle states for all the different momenta k, and the space of positive frequency solutions. So we've got the map is given by this. Well, obviously, we define our Minkowski vacuum state as the state which is annihilated by all this annihilation operators for all the different momenta. The one-to-one mapping is via this Minkowski vacuum state, and as I say, it's between the one particle Hilbert space and the space of positive frequency solutions. So you've got an element of the Hilbert space, and the mapping is just naturally given by this linear combination of the bases, or the complete set. So the UKs form a complete set of solutions of the triangle equation. So that's the one-to-one mapping between F tilde, an element, a one particle state, and solutions. So a solution of a positive frequency solution of the triangle equation. And then, so we've got the Hilbert space, we need an inner product. So the inner product is just given by this. Where df, I gave this expression last week, dfk's and jk's are just the Fourier mode coefficients in the expressions of f and g in terms of the complete basis. Well, I think I made the typo last week, in fact. So f tilde is given by this. So the complete basis of the one particle states. The case just one, it's a one particle state of momentum, a quantum of momentum k, and you integrate all of them, the coefficients given by the f tilde k's, it just goes in here. And the same thing for g, of course, you've got replace this f by g. Yeah.
Is the omega k squared the definition there?
I think so, yes. Thanks. So this is just a recap of what we've done so far. Okay, so just the same way, we've got the one-to-one mapping between H1 and P. We've got an inner product. This is your inner product in the Hilbert space H1. And then I'm going to establish a relationship, in fact equality, between the inner product in this space and one in the space of positive frequency solutions. So that's what we'll do next. So let us now look for an inner product in P. Okay, in order to do this, we're going to go to, I'm going to define the momentum. We've defined field phi, and field phi has got an associated momentum. Canonical field momentum. So first of all, we do it by classical theory, and that just defines as the partial derivative of the Lagrangian density with respect to phi dot. Dot always denotes derivative with respect to time. For the case, so what's phi dot in the case that we're looking at all the time? It's real scalar field. Well, it's quite trivial. So for the case of a real scalar field, so remember the Lagrangian density was given by this plus other stuff that it did not contain derivatives. We're in flat space-time, so this is just eta nu derivatives of phi. Again, we're in flat space-time, the covariant derivative is just a partial. Well, you don't even need to be in flat space, and the covariant derivative of a scalar is just a partial derivative, so this is just equal to this. So we have the Lagrangian density is minus 1/2 of eta v nu is minus 1, 1, 1, 1. So all I'm interested in here is the partial derivative with respect to phi dot. All I want is the derivative with respect to time. So the only derivative with respect to time will be a minus phi dot squared plus all the stuff which does not contain phi dots. Sorry, it's plus because, oh, minus, no. Oh yeah, that's correct. So minus plus, so that's plus phi dot squared over 2 plus all the stuff which does not contain phi dots. And so that tells you the momentum is just phi dot. For the particular case of a real scalar field. Any questions? Okay, let's take the commutator between phi and time, between the field and the momentum. Okay, this is the commutator between the field and the momentum at equal times. Okay, there's different spatial position at the same time t. So let's put in the values for phi and for pi. For phi, phi we've got this, and for pi is phi dot. So you take the derivative with respect to time of this. Okay, so we're going to have the same. But if you differentiate with respect to time, bring down the coefficient here, so that's minus I omega k prime, and the same thing for the other one. Okay, now you use the combination relations for the A's. and 0 for AA and A diagonal. So computation between A and A will be to 0. Between A diagonal will be to 0. Between A and A diagonal, it won't give you 0. So we have to put together these two. And between A diagonal and A, that will not give you 0 either. Now, the commutator between A and A dagger is minus the commutator between A dagger and A. So you get a minus sign in this one with respect to this one. But also, you have a minus sign here that you don't have there. So the two minus signs will cancel out, and you just have twice this. So, so that's going to be, well, and the delta will get you through one of the two intervals. Okay, so you're going to have just one interval. Now the k and the k prime are the same. So omega k is equal to omega k prime, so you just have 16 pi cubed omega k. K and k prime are the same. So these two will cancel out, and these two will cancel out. Sorry, x. This is x prime here. This is x prime. So the t's are the same. So the exponential t and the minus exponential t will cancel out. The x bits will not cancel out because we've got x and x prime. So we've got exponential of ik x minus x prime. And then yes, and then 2I omega k. Okay. And the one operator if you wish.
Okay, we are already using that the commutator of AK and AK prime is delta K and K prime.
Yeah. That allows me to go through one of the intervals, the k prime. Okay, so the omega k's cancel out. There's 2 and 16. And that just gives you delta x minus x prime. Do the same thing between phi at tx and tx prime. You do the same thing between pi tx prime, and you get those to be 0. Okay, so you can do them. So I write this one again. and the other ones are 0. These are called the canonical commutation relations. Or equal time. Commutation relations. You can try this as exercise. It's just very similar to what we've just done. Are these satisfied at all times or just a specific time? At all times. We haven't included here any specific time t. T is just arbitrary time. So this is valid. If it's valid at one time, and if this is satisfied, then this is valid at one time, then it is valid at all times. Is it valid for any choice of time? If you choose a different time that's not the time corresponding to Cartesian coordinates, if you choose some crazy time, is it still valid?
Not sure.
Okay, what is it?
There will be a problem with the background.
Yeah. So it is not clear, as we've done it, it's not clear that is true. I'm not going to really be bothered about that for now. I will be a little bit more specific about this when I do the core spacetime. But the answer is yes, this is independent of the frame that you choose. If you're choosing specific foliation of the spacetime in terms of this coordinate time t, if this is satisfied, so this will be independent of if this is satisfied for a certain time, given a certain choice of time at a certain time, then this will be satisfied for any choice of time and at any time of that time. Okay. We'll see this specifically when we go to curve space. Anyway, but this is very important. But what we were set off to do was to look for the inner product in the vector space of positive frequency solutions. Okay, so now we can do it. These are just general solutions of the Klein-Gordon equation. And we define the inner product for solutions of the Klein-Gordon equation in the following way. There's a choice of frame, T, coordinate frame, and a particular value t0 of that time. So it's easy to check that this is a scalar product. So you can try this as an exercise. Now, we need, in order to, so we have a one-to-one mapping between the one particle, the Hilbert space of one particle states and the positive frequency solutions. So we want, and we have an inner product in the H1, we want an inner product for the solutions as well. So apart from being a scalar product, is this also an inner product?
Yes. What is the difference between a scalar product and an inner product?
So you're saying yes, we have no idea the difference. Positive definite.
Sure.
So
Scalar product
that's crucial.
isn't positive definite. Inner product is true.
Sorry?
What is the difference between
The inner product is a scalar product which is positive definite. So is this an inner product? Or in other words, is it positive definite?
I would have to do a lot of calculations to check for that.
Sorry?
I don't know how to see it just for looking at the expression.
Okay.
And I won't do.
Let's see now. Let's see if it is or not. So let's take a scalar product between two elements of the complete set. Okay, so I gave the value for the complete set earlier on. We've got for BI and then 16 pi cubed, the normalization factor, square root of omega k, square root of omega k prime. K and k prime are not the same. By the way, there's a shorthand notation for this. So the notation is this is the shorthand notation for this. So first of all, you take the partial derivative with respect to t on the vector on your function on the right, and this one has an arrow to the left, meaning that then you take it minus the same thing, but you take the partial derivative with respect to the function on the left. So I write this here. In here, we don't need t equals to 0 anymore because the other time dependence has gone outside. Integral with respect to x, this factor is independent of x, so this is just a delta drag distribution with a factor of 2 pi cubed. Now, if you have something times a delta of x, if you have a function of x times a delta of x, you can set to x equals 0 that function multiplied by delta. Okay, so in this case, the x equals 0 means k equals k primed. So we can set k equals k primed everywhere the factor is relevant. Okay. So this means that this becomes omega k. Omega k is positive valued. This will become minus 2i omega k, and so the omega k here cancels out with the 1 here. Omega k minus omega k, that just gives you 1. And the 2 pi cubed, together with the 2 here, cancels out the 16 pi cubed here. And the minus I cancels out with the I. So that all there's left is the delta cube. So a few interesting features. First of all, this tells you why in the UKs we chose the normalization as given by this square root of this. We chose that so that here we get a neat delta cube Dirac distribution. Okay. You didn't have to choose this normalization for the UKs. You could have chosen without the 16 pi cubed. Then you would have a dirty factor here in order, which is fine, which is not neat. So in order to not have any factor here, in order to just get the delta cube, that's the reason why we chose the normalization as we did for the UKs. That's number one feature. Number two is this positive definite. Okay, this positive definite. So far so good. And another very important feature, which is this was for some time t0, yet this is independent of time. Okay? So this is independent of the choice of time t0. So what that tells you is, if you have two functions which are orthonormal at some time, it will continue to be orthonormal at all times. So that's very important. Throughout the whole evolution, you're preserving orthonormality of solutions which are orthonormal in the start. Still on the positive frequency, these are solutions, these are general solutions. Now UKs are positive frequency solutions. They're bases. They're a complete set of positive frequency solutions. And they are positive definite. Now remember, the one-to-one mapping that we had was between H1 and not the full set of complex frequency solutions, but just the positive frequency ones. So we have an inner product here So the question is, if now I take UK's star, and these guys are now negative frequency stations, is that going to be positive definite?
Yes.
Right?
Isn't it similar to the complex conjugate of the reciprocal?
No. Well, yes, but you have to be careful about this. Because taking the complex conjugate of this is not the same as taking the complex conjugate in phi 1 and phi 2 because there's an I here. So you're going to have a change of sign. So do you want to rethink the yes?
Sorry?
Do you want to rethink the yes to this being positive definite? Based on what we just said?
I think it is, but not based on what I said. The result for the new case will not depend on the frequency.
On frequency, no.
Only on the omega units.
No.
It's only
Yeah, but is this going to be positive definite or not? You're saying yes, but what I'm saying is, you take the complex conjugate of this, that will remain the same, but our randoms have real values, so the randoms have one change. So what is taking the complex conjugate of this equal to? It's equal to the complex conjugate of this, which is equivalent to changing complex conjugating phi 1 and phi 2. So complex conjugating UK and UK times. But also, you have to complex conjugate this. So you're going to get a minus sign. You can do the, so that's one, so I just proven to you that it's not positive definite, it's negative definite. One. Number two, you already had a hint here in the fact that the one-to-one mapping is between H1, so inner product is between the one-to-one mapping is between H1 and P, not S or not P bar. So it's between H1 and the positive frequency switches. So really you want, and you have an inner product here, so you want an inner product in P. Not necessarily in S. Okay? You can do it even more explicitly if you wish. Just take the complex conjugate here. All you're going to do is you're going to change the signs here. Okay, so you're going to get minus delta cubed. You can do it even more explicitly if you wish. And if you take it between UK and U star K and, well, what we're going to get is 16, so a lot of it is the same, 16 pi cubed. And now in here, you get to change the sign of one of them. The sign of the K prime. Okay, so you get the sign of the K prime. Say change the sign of the K prime as well in here. So that's K plus K prime. So that tells you that you need K equals minus K prime, but still omega K is equal to omega K prime. Okay? Omega K only dependent on the modulus of K of the vector K, not on the sign of it. So that tells you that this will be to 0. So this scalar product is positive definite for whenever you choose solutions which are positive frequency. It is negative definite whenever you choose solutions which are negative frequency. And this is, we've shown this for a complete set, and so any negative frequency solution is a linear combination of the complete set, and so this is also true for the general negative frequency solution. So this guy, this scalar product, is an inner product only for the space of positive frequency solutions. So really, your Hilbert space is constructed from the positive frequency solutions. When I say it's constructed from positive frequency solutions, well, that's not exactly it. There's a one-to-one mapping between positive frequency solutions and the elements of the Hilbert space. Okay? Because of the one-to-one mapping, people say they use indistinctively positive frequency solutions as elements of the Hilbert space. Also, we've defined an inner product in H1, we've defined an inner product in P, and they actually happen to be the same, so I'll show this next. So, furthermore, this inner product is the same in the following sense as the standard So let's show this. I'm going to take a positive frequency solution. So I just wrote this to start. And then the definition of the phi case of this is, it's a linear combination with some coefficients fk of this. Okay, these are proportional to the complete set. And I showed last week, and I reproduced it at the start of the lecture, that this is equal to this. So now you can just read off these coefficients phi fk. They must be equal to this. do the same thing for another phi g and phi f, and one particle state g, you get exactly the same thing. And now you take the inner product between these two positive frequency solutions. Okay, that's the definition of the inner product. I don't even put in t equals t0 here because we've seen that it's independent of time. So far, it's quite trivial, straightforward. Okay, so we have, so I can take the x integral inside, so this is what depends on x. So that just, again, that's G delta. This factor inside in the integrand, what does it look like? Phi star phi dot minus phi star dot phi. That's like a Vronsky. When k and k prime are different, then it's not really Vronsky because you've got different potentials in your harmonic oscillator equation. But when k is equal to k prime, the potential in your harmonic oscillator equation is the same. And so this is exactly the Vronsky. So the Vronsky Vronsky between two specific solutions, phi star g Vronsky. Now, we've got the delta cubed from this, from here. Any coefficients of the delta, you can set k is equal to k prime. So we can set k is equal to k prime in this factor, which just gives us the Brownian. And I'm missing the 2 pi cubed, which cancels out with this one here. So that's what we have. We can still keep calculating this. The derivative time derivative of phi is just from the harmonic state equation. Is equal to this. So we've got a minus I omega k coming down from each one of these two. So there's a dot missing here. Okay. So there's got a minus I omega k coming down from here, another one from here. And that gives you, because the k's now are the same, that gives you 2 times there is a there's minus I coming down, which cancels out with the I. Okay, so there's an I, so 2 minus I times I, which is just plus 1. Omega k, and then the 2 solutions without any derivatives. Okay, now we can write the explicit values for this. Explicitly this phase. This is from here, call this equation star. I've written in the star equation both for n and for g. Okay, 2 omega k. Omega k is positive, so you can do this. I omega t cancels out with ei omega t cancels out with e times I omega t. So get this. What is this? Sorry?
Unit product of
Inner product of what? Yeah.
F.
Yeah. So that's right. So we started off with the inner product for that we define for positive frequency solutions, and we're ending up with the inner product for the one particle states. So this is just G tilde X tilde. Okay. So this is what I said here. The inner product in P is the same as the standard inner product in H1. Okay, so we have a one-to-one mapping between one particle states and positive frequency solutions, and the corresponding inner products are the same. Any questions? This inner product for the solutions, in fact, the scalar product for the all solutions, not just the positive frequency solutions, allows us to find the Fourier coefficients of the solutions in terms of inner products. So the scalar product note that I'm talking now about a scalar product in S, not an inner product in P. So I'm referring to the whole S. So this allows us to find the Fourier coefficients as inner products. So you take the inner product of UK and your general solution phi, for which you want to get the Fourier coefficients. I'm doing this at the classical level. Okay, so inner product with the first one is UK prime. And the second one, the complex conjugate. So this, we found these things. So this guy is 0, and this one is just equal to this. And so this just gives you AK. Okay, so that's how you get the Fourier coefficient, by taking the inner product between one element of the complete set and the solution, the general solution. You do the same thing for the other one, for the complex conjugate one. So similarly, AK star is UK star times minus this. Okay. minus again arising because of the I in the inner part. The scalar part, because I'm including negative frequency solutions here. So whenever you're building your quantum field theory, you need to determine your positive frequency solutions. They're the ones that are mapped one-to-one to the elements of the Hilbert space. Is this complete set, the complete set that's formed by the UKs, is that unique? Why not?
The other set of phases, like,
Yeah. So what other one could there be?
I don't know, but I know that a set of phases is not unique.
Have you know?
You can take several linear combinations of this set of phases from another set of phases.
Okay, so this comes, remember we had this, and then we made a specific choice of coordinates. This is totally covariant. We made a specific choice of coordinates. We chose a Cartesian frame and a time in that Cartesian frame. And that's how we build the UKs. Okay, as proportional to minus I squared minus I omega k equals I omega plus I kx. Okay. This privileged in some sense the Cartesian time. But like Joao says, you can take any linear combination of this. In fact, you can combine UKs and UK stars if you want. And that will still give you, you can build another complete set from those. From a more physical perspective, you could have chosen a different time here, and we will do that later on. Choose a different time. And choose positive frequency solutions with respect to that time. Remember, positive frequency solutions just means that you do a Fourier model decomposition of your solutions, and that just gives you non-zero whenever the frequencies are positive. Whenever you do a Fourier model decomposition, you're doing that with respect to a time. Okay? You take your phi's and then you decompose them with respect. This is how you find your Fourier modes. You decompose them with respect to some time. In a Fourier model decomposition, is a choice of time. Whenever we say positive frequency solutions, we're saying a choice of time. In here we chose the Cartesian, the time corresponding to the Cartesian frame. You could have chosen another frame corresponding to another observer if you wish. And that would give you another concept of positive frequency, and it would give you another complete basis. We'll see this explicitly later on. This is very, very important. But the point is, this set is not unique. You can have different sets. And so, I'm now going to give you the prescription for building your QFT in flat spacetime, which is summarizing what we've done, but I want to write it in general for a basis, a complete set, which is not necessarily the UKs that we've defined. So to summarize, but also generalizing, to complete, to a general complete set. The canonical, we're doing canonical quantization. The first thing you do is you choose complete set. Of homogeneous solutions of the field equations. And you choose them, you want to build your positive frequency space. So you want to split them into your positive frequency solutions and the negative frequency solutions, or even more fundamentally than that, solutions which have positive norm and solutions which have negative norm. Remember, in order to build your Hilbert space, you need an inner product. That means scalar product which is inner, positive definite, and so you want to choose your solutions which have positive norm. Okay? We've seen how in this case, the UKs have positive norm, the UK stars have negative norm. The really important thing is you want to split your complete set into positive frequency solutions and negative frequency solutions. So some UIs which are positive frequency and complex conjugates of that which will be negative frequency. Okay, so I'm writing this in a general way. So as I say, not necessarily the UKs we've seen. So in particular it can be the UKs we've seen, but it doesn't have to be. You choose another complete set. And the I index is just a total general index here. It can be discrete, it can be continuous. It doesn't really matter. If you've got UKs, it's going to be a continuous index, and so this delta here, it's not going to be a delta chronometer, it's going to be a delta drag. Okay, so this is a general notation to include, encapsulate both cases. The case where the index is continuous or the index is discrete or continuous index. Okay, just in the case that it's continuous, this will be the delta drag distribution. So this is delta chronometer or drag, depending on whether we've got a continuous index or a discrete index. It's just a general notation. Okay, so that's the first step. So let's do classical. Okay, we've got classical field equations, classical field. You just choose a basis, choose a complete set in that way. The second step, a general solution of the field equation write your general solution as a linear combination of this complete set. This is, of course, we're doing all this for a real scalar field. So that's why we have the complex conjugate to make it real values. Again, the summation here, if it's a discrete set, if it's a continuous set, that's going to be integral. This is just general notation to indicate either. we can find the coefficients, the Fourier coefficients, via scalar product in that way. Okay? We still haven't quantized. The next step is to quantize. But review it. Whenever you write about this, you're writing it as a combination of harmonic oscillators. The AI is being annihilated, the A stars. The A-timers are creating quantum in that harmonic oscillator. So quantize. And you quantize by promoting this Fourier coefficients to the operators in this way, and obviously the field. And impose the equal time commutation relations. That's the ones that we've seen. And this is equivalent to the commutation relations for the A's and A-diners. Okay, so this prescription is coming from the harmonic oscillator, and we've seen that that's equivalent to imposing these commutation relations on the equal time commutation relations on the field and the canonical momentum. This is just the QFT equivalent of QP equals 1 in quantum mechanics. And then the last point is you just build your Hilbert space. So you find a vacuum state. Now I put this in quotes. I don't really like the use of vacuum. It's vacuum in this particular sense, but it's annihilated by the AIs. And then the one particle states, you build them by applying to this vacuum state, and you build, that gives you the one particle Hilbert space, and from that you get your full fog space. So this here is one of the most important things we've done so far.
Step number one, you wrote linear product between ui and j equals delta ij. And then you wrote the same thing but now equals to 0.
Yeah, that's wrong.
Stop.
Thanks. We've seen this for the particular case of UKs, just using general notation for an arbitrary complete set. Any other questions? Okay. So, we've seen that phi